Okay, welcome to tonight's class. We have two things on the agenda for tonight. The first one is that I want to talk about non-homogeneous systems of equations, and we'll be doing that by means of example. And then I'd like to do just a little bit of work on nonlinear and nonlinear systems. And we'll be looking at predator-prey systems and things that are similar. And also along the way, we will be using some technology which you've already seen in previous lectures. But we'll be looking at phase plots and making use of the Wolfram Alpha website. So, here we go. The first one is this, y1 prime is equal to y1 plus y2 plus t, and y2 prime equals 3y1 minus y2 minus 3. And the thing that makes this non-homogeneous is these terms right here. So these are non-homogeneous systems, and if you wanted to write it in the vector form and in a way that looks like what we had for a single equation, it would look like this. Y prime minus cap A, some matrix, times y is equal to a vector r on the right-hand side. And in this particular case, since we have a specific equation here, we actually can write down all of these pieces. The A is this matrix 1, 1, 3, minus 1. And we're multiplying that by y, which of course is a two-component vector, y1 and y2. And then we are setting that equal to a right-hand side, which is the vector t and minus 3. Now, I'm sorry to say that I worked all of these ahead of class, and I was rudely reminded of how tiresome some of these can be. They really take a lot of steps. The thought is not deep once you know the secrets, but sometimes the arithmetic and the algebra can really take its toll after you do a half dozen or so. It really can take some work to get through it all. So if we're going to solve this system, the first thing we need to do is to find the homogeneous solution, YH, and we're going to do that by computing the determinant of this matrix with subtracting lambdas down the diagonal. So just the very things we've been doing. So you subtract lambda down the diagonal and take the determinant of the resulting matrix. And what we have here is, we're going to take this product, but to me, it's easier if you think of it this way. Take a minus out of here and bury it in here. And then you got lambda plus 1 times lambda minus 1. Well, lambda squared minus 1 is the result from algebra. And then we subtract the product from this diagonal, minus 3. So we have lambda squared minus 4 is equal to 0. So if we could factor it, lambda plus and minus 2, or we could push the 4 on the other side and extract roots. But lambda 1 and lambda 2 are plus 2 and minus 2. So we can write down the homogeneous, the solution to the homogeneous equation immediately. Oh, no, we can't. Whoops, not quite there. We need our vectors, right? So these are the eigenvalues, and now we want to get the eigenvectors. So what I'm going to do is start with the matrix A, and I'm going to subtract the one eigenvalue at a time, of course. So this is the one for lambda equals 2. I'm going to subtract 2 down the main diagonal, and I should get a singular matrix. And then I want to find a basis, a convenient basis of its null space. And for 2 by 2s, it's pretty straightforward. Generally, you can just kind of look at them and see. If not, you say -1 times x1 plus 1 times x2 equals 0, and then you solve it. Find a solution, just any solution. Clearly 1, 1 here works. If I take 1 times this and 1 times this and add them up, I get 0, same on the bottom. So that is the eigenvector, I'll call it x bar 1, that goes with lambda 1, which is equal to 2. So that's a pair. Lambda equals 2 is paired with the vector 1, 1. And I can repeat this for, maybe I'll repeat it down here so I don't run out of, so you can see what I'm doing. I'm going to repeat this for lambda equals 2. Well, if I subtract -2 down the main diagonal, I'm adding 2. So starting with that matrix right there, I'll have 3 and 1. And the off diagonal elements don't change, 1 and 3. And once again, you can probably just look at it and find a convenient form of the eigenvector. 1 minus 3 would work. And so that is x bar 2, and lambda 2 is -2. So I've got my pair of eigenvector pairs, and now I can write down the homogeneous solution directly. YH is equal to any constant, and that's a scalar constant, times the first eigenvector, 1, 1, which is here, and then e to the 2t, where 2 is that eigenvalue. And then C2, take a look then at the second eigenvector, 1 minus 3. E to the -2 is the next eigenvalue times t. So there's the homogeneous solution. And now our goal is to get a particular solution, something that when plugged into this equation here would produce the t and the -3 in this right-hand vector. Well, this is linear, and these coefficients are constant. So what we're going to do is just undetermined coefficients like we did with single equations. It's just that, you know, you have to do everything with vectors. So if you think about what a general linear function would look like in with vectors rather than with scalar quantities, it would be something like this. Some constants in this vector times t plus just a constant vector here. So in other words, a first degree polynomial should be capable of producing first degree polynomial terms on the right hand side. So what we're going to do is take this form right here and simply plug it into the equation and solve for the unknowns. Now, unfortunately, there are 4 unknowns, right? And it's only linear. So you can imagine if you had like a second degree term on the right-hand side, you'd have 6 unknowns. It can get unwieldy, but the method is really very similar to what we did with single equations. So let's go after it. Let's see. What we have here is y bar prime equals a, which is 1, 1, 3 minus 1, times y plus the right-hand side is t and minus 3. And we are projecting, hypothesizing that a particular solution will have the form of a linear function, but the coefficients are constant vectors rather than scalars. So u1, u2, t plus v1 and v2. Okay, so what we do is simply plug this into that and try to clean up the mess after we get that done. So if I take the derivative of this function here, well, the only thing that has only variable in this is this t. So the derivative of this function is just going to be the constant vector u1, u2. Derivative of a linear is a constant. So on the left-hand side, I have u1, u2 is equal to, and now I am going to plug this mess into the right-hand side. Well, and that means essentially plug it in right there for y. We can do this a term at a time. So when we multiply this matrix times this vector, we're going to get this vector, u1 plus u2 on the top. And then we'll get 3u1 minus u2 on the bottom. And of course, that will retain the t on here. It's just a constant multiple, scalar multiple of this vector. And let's leave it on the outside. It'll be easier to keep track of. And then when I take the matrix times that constant vector, I'll get this vector, v1 plus v2, and 3v1 plus v2. And then when I add the vector with components t and minus 3, everything's supposed to be in balance.
It'll be 3v1 minus v2.
Did I do one wrong? I did. Thank you. Did I get? Yeah, I got the minus on that one. Okay, well, let's push everything but this t minus 3 vector to the left-hand side, and we'll just try to gather things up as well as we can. Now, notice that this is the only vector that has a t on it. So that's already simplified. We've got in the top row, let's see, minus u1 plus u2 t. That'll be this one once you've pushed it over to the other side of the equation. And then we'll have some constants. Those are, we're subtracting the v1 plus v2. And then we already had a u1 on this side. And that has got to add up to be t, because that's what will be here. And in the same way, just looking across the bottom row now, we have minus 3u1 minus u2 times t. There's the t term, and then the constant term is going to be subtracting this, 3v1 minus v2, and then we already had a u2 here, so plus u2, and that's supposed to add up to minus 3. And we hope this gives us a system of equations, and it does. Notice, you could say it this way, this is t plus 0. So the coefficient on t on the right is 1, and therefore that thing is equal to 1. The constant term on the right is 0, so that sum is 0. And likewise, this coefficient must be 0 because there's no t on the right, and this stuff must add up to minus 3. Now, you could set up a system of equations, but I'm thinking that this might go okay if you don't. Let's see what we can do here. I know that this coefficient right here is 0, right? Because there's no t on the right-hand side. So I'm going to focus on this for the time being. 3u1 minus u2 must be equal to 0. And in the same way, I know that this one right here, u1 plus u2, well, that's inside the parentheses with a minus on it. But when you do all that, it's got to come out to be plus 1. So what's in here must be minus 1. And I think we can start picking off some low-hanging fruit here on our system of equations. If we add these two up, we get 4u1, and then minus u2 plus u2 drops out to 0, and I get minus 1 here, which tells me that u1 equals minus a fourth. Once I know that, then I can get u2 as well. Let's see, how about if we go with this one right here? So if I take u1 is minus a fourth, plug it in here, I get minus 3/4. Well, then you'd want plus 3/4 in order for this to add up to 0, so that u2 would be minus 3/4. I think, let's just double check. If I take the sum of those, I'm supposed to get minus 1, and I do. So I've got u1 and u2. How about v1 and v2? Well, let's see. We have u1 and u2 sitting there. So how about this then? If I take the negative of v1 plus v2, do I want to do that? Let's write it this way. v1 plus v2, I know that this whole thing sums up to 0. That's what I'm working with. So if I actually just multiply that equation by minus 1, then I get v1 plus v2 minus u1 is still equal to 0. It's negative 0, but that's 0. And the good news is I know u1. So v1 plus v2 is equal to u1, and u1 is minus squared. And how about this one down here? Reasoning in the same way, 3v1 plus v2 then I'll put the, well, I'm taking the negative already, so I've got a 3 over here from this, and then I subtract u2, but u2 is 3/4. So it looks sort of like that. And we can hope that there are no arithmetic errors so far. There's a lot going on. Is there an issue?
Is it supposed to be 3v1 minus
These have opposite signs. So if this is a plus, 3v1 minus v2, yep, minus v2, and then I'm going to add u2, then this is a minus 2, correct? I maybe compacted that into too few steps. Let's write this out again. Minus 3v1 plus v2 plus u2 equals -3. That's where we start from. And then I multiplied it through by a negative. 3, and then it will be plus u2. And plus u2 is subtracting 3/4. So 3v1 minus v2 equals 3 minus 3/4. And be 2 1/4, 8. 9/4. Whoops, I'm on the wrong one. So v1 plus v2 equals -1/4. 3v1 plus v2 equals 9/4. Okay. Well, I guess similar to what we've done before. How about if we subtract this equation from this one? Then we'd have 3v1 minus v1 would be 2v1. This one minus this one is 0. 9/4 minus a minus 1/4, 10/4, which is 5/2. So 2v1 equals 5/2, v1 equals 5/4. Now, if all of this is correct, then I've got another solution here. I've got another equation here. v1 plus v2 is -1/4. So v1, which we now know is 5/4, plus v2 equals -1/4. And so v2 equals -6/4, which is -3/2. Okay, so I got v1 and v2, I hope, and I have u1 and u2, and that's all there was to find. So yp, assuming all the arithmetic is correct, is the vector, oh gosh, it was off the screen. Sorry. Is the vector u1, u2 plus the vector v, and v is 5/4, v2 is -3/2. So that is certainly the way it's done. But as you can see, there's a lot of room for calculational errors, dropping minus signs, forgetting your place, and plugging the number in the wrong one. All sorts of things can happen. Now we could check this. If you plug this in the original equation, it should work, right? But we've already got several minutes on this, and there's several to go. So this is the way it's done, and I encourage you to look through it carefully on your own after class and make sure that there isn't a bug in it. But I think we've got them all. Oh, I suppose I should say, just to make sure we're all on the same page, then the general solution is the homogeneous solution plus the particular solution. This is the particular solution. The homogeneous solution is the one that we did first. And that's got the arbitrary constants in it. So there's YH. Okay, well, as advertised, you do it pretty much the way you do for a single equation. It's just that the arithmetic can get really intense. So here's another one. And in this case, we have a right-hand side, which is an exponential. So I want to work through at least one of those. By the way, I computed the homogeneous solution myself. And it was like this previous calculation that we just waded through. It actually is not, it's not deep. We don't do anything that's particularly hard in and of itself. It's just that the arithmetic is pretty intense. So I'll just start by stating the homogeneous solution, because the only thing we need it for is to make sure that this term doesn't collide with one of these, and it doesn't. These exponents are e to the power 2 plus root 5t and e to the power 2 minus root 5t. You recognize those as things that would come out in solution of a quadratic equation. And that's what it is. So, and we just get the eigenvectors in the usual way. So the only use I'm going to make of this is to say, there it is. I computed it in the usual way. But I'd like to sort of get to the point, which is for this one, we have this kind of a form, y bar prime minus a y bar equals a right-hand side, and the right-hand side is a constant vector times an exponential. And this exponential is not a part of the homogeneous solution. So what do? We say, well, for if this is a linear equation, and it is, then we would expect that the particular solution would have this kind of a form, some constant vector times e to the minus 3t. Now that would be reasoning directly in analogy to what we do with the first order equations. It turns out though that this is not always good enough. For systems of equations, you have to consider the possibility that you may need a constant term as well. So I suppose I should have used u here so I could follow the pattern from last time, but I didn't. So let's call this A1 and A2. And what you do is just what we did before. You plug this yp into this equation, generating a tremendous mess. What you hope that it really simplifies by the end, and you just get a nice equation, a nice function of this form. And if we're lucky, you know, maybe the constant will drop out or something, and it might. Okay, well, if we took the derivative of yp, then this is just constant, right? So if you take the derivative of that, you get the zero vector. That one goes away. When you take the derivative of this, the only t in here is in this scalar. So you get a chain row factor of -3 and nothing else changes. So the y prime part is this, -3 v1 -3 v2. That's the chain row factor popping in here. And then you've still got an e to the minus 3t multiplying that term. Okay, so that takes care of the y prime. Now I want to subtract off what I get when I multiply this vector and this vector by the matrix A. So I'm looking way up here for A. So v1 and v2 multiplying this vector, I get v1 minus 2v2. And minus 2v1 plus 3v2. And of course, this vector is still multiplied by e to the minus 3t. And then when I multiply this constant vector a1, a2 on the left by this A matrix, I pick up a constant vector term, and that is a1 minus 2a2 and minus 2a1 plus 3a2 Okay, so what I've written so far is y prime, that's this, minus a times y, except I forgot to write my minus sign here, so let's just insert that before it gets lost. Minus ay, that's this, and then that's equal to the right-hand side, which is 2 minus 4 e to the minus 3t. And let's see. Okay, well, in this case anyway, it's pretty clear that this whole vector is going to be the 0 vector, right? Because everything else has an e to the minus 3t in. So scrap that. Now, what kind of equations do we get here? We get minus 3v1 minus v1 again plus 2v2 equals 2. And absolutely every one of these is multiplied by e to the minus 3t. So you can just drop that. You know, you can put it on every single term and then divide it out, but that isn't very efficient. Minus 3v2 plus 2v1 minus 3v2 is equal to minus 4. And this should simplify nicely. Let's see, we've got minus 4 v1 plus 2 v2 equals 2, and 2v1 minus 6 v2 equals minus 4. And we could work with it in that form, but since there's a common factor of 2, why don't we take that out? Actually, why don't we take it out of the first one and not the second? That will be convenient. Dividing this one through by 2. Minus 2v1 plus v2 equals 1, and 2v1 minus 3v2 equals minus 4. Now, when I add those up, v1s add out. I got minus 2 v2 equals minus 3. So v2, I get 3 halves. I see you working with the calculator. Did you put the system in?
No.
Oh, okay, okay.
Just don't feel like doing addition in my head right now.
Yeah, that's fine. I thought maybe you had to take the system in, and I just wondered if you got the same result. Okay, so we got V2, and then it's not a problem to get V1, right? So we got, I don't know, let's take that first one there. 2 V1 plus V2, which we now know is 3 halves. Yep. It is. Yes, it is. Thank you. That makes that all wrong. So this plus this still adds out. So I get minus 5. V2 equals minus 3. Now what happened here? What did I have in there before? 3? I guess I divided it by 2. I can't imagine why.
Yeah, I think you divided the top by 2, and then you said that the second one will remain the same, but you did divide the one term by 2.
Yeah, well, there's never really great logic behind mistakes, right? So, there wasn't in this case. So V2 equals 3/5. And now I think we have 2V1 plus 3/5 equals 1. I'm working from this equation here. So minus 2V1 equals 5/5 minus 3/5 is 2/5. Dividing through by minus 2, V1 equals minus 1/5. And we earlier decided the A's were just zeros, so we don't have to worry about those. I think we're there. So it looks like YP equals V1, which is minus 1/5, V2, which is 3/5, times, and remember, all the way back where? All the way back here, I'm assuming that it's that V1, V2 vector times e to the minus 3t. E to the minus 3t. And if you plug it in, it should work. And YH, we didn't compute, but I did give it to you. At least I gave you the version I got earlier in the day, which is this guy right here. And by the way, if you were doing this and it just really got ugly, you know, there's no reason you couldn't type it into MATLAB or something and just ask for the, you know, give me the eigenvectors and give me the eigenvalues, and you get decimal approximations to this. And in most practical situations, that's plenty good enough, because you can run out, you know, as many decimals as you need. So, and by the way, once you get that done, if you're like in an engineering situation or I don't know, experimental situation in physics, sooner or later you start machining parts and weighing masses and stuff like that. Well, that work is not perfect either, right? It might, in fact, be very high precision, but it won't be perfect. So if you can get enough decimals, it's fine. You're good to go. Okay, so that was the second one, and now why did I pick this one? Since it seems to be a repeat of what we had before. I don't know, and I don't think we're going to have a lot of extra time, so let's go for variety. Okay, what if you had sines and cosines on the right-hand side? Well, you probably pretty much know what to do, right? I assume that I can create those with some sine and cosine terms, and I put them in the equation and hope everything works out. So I will be looking for, why don't we just go direct for the particular solution here? I'm looking for a particular solution. And by the way, that's perfectly safe for this reason. I know the particular solution is going to involve sines and cosines, but what's over here, this is, if I just took those off, I'm not expecting a pure sine or a cosine here unless I had eigenvalues that were pure imaginary. And let me just check here. I think we're good. So you could, oh gosh. I'm not absolutely sure. I'm relying on memory, of course. So maybe I should just check before before I plunge ahead and make an assumption that can't be fulfilled. But I think if this were sines and cosines, I probably would have simply chosen another example. Okay, so this is equivalent to 4 plus lambda times lambda minus 1, putting a minus sign on each of those. Lambda plus 4, lambda minus 1 equals lambda squared 4 lambda and minus lambda, 3 lambda. Yeah. And minus 4, I think. Yeah. And then we got to subtract 6. Okay, so we've got lambda squared plus 3 lambda minus 10 equals 0. Lambda equals negative b. Let me see. Does this? Oh, it factors, doesn't it? Lambda minus 2 and 5. One of those is positive, but we'll figure that out in a minute. Plus 5. So that factors, and therefore the eigenvalues are 2 and minus 5, meaning e to the 2t and e to the minus 5t are the basis functions. And I'll have those multiplied by some vector. But the point is, there's no sine or cosine. So we're okay to jump ahead here a little bit to find yp. Okay, so yp should be something of this form. And unfortunately, this is truly messy. How about this? A1 cosine t plus A2 sine t. And on the bottom, I'll call that B1 cosine t plus B2 sine t. Now, there's nothing special about A and B. I'm doing it this way so that I'll just remember when I get to the end. If I've got an A, that went on the top row, and if I got a B, it's on the bottom. But you could call them A, B, C, D, or whatever you like. And the goal here is just to plug them into the equation. Unfortunately, it is not really nice. Okay, let's take the derivative of this. When I take the derivative of this, I'm going to get minus A1 sine t plus A2 cosine t. When I take the derivative of the bottom one, I'm going to get minus B1 sine t plus B2 cosine t. And that accounts for the y prime term, which is on the equation, that's the left-hand side. And I could just, for now, write it as it's written up here. So I want my matrix, how about if I write this down here where it'll show on the screen? 1 minus 2, 3 minus 4. I'm taking that matrix times this vector. So I get, let's see, 1 times all of this minus 2 times all of that. Okay, here we go. 1 times the top entry minus 2 times the bottom. Minus 2 B1 cos t minus 2 B2 sine t. And then we do that again with the bottom row of the matrix. So 3a1 cos t plus 3a2 sine t minus 4b1 cos t minus 4b2 sine t. And that is yp times the matrix A. And then there's yet another term on this. We have to subtract the vector sine t cosine t. So this equals this minus that. Oh, good heavens. All right, well, let's start putting these pieces together. This is complicated enough that what I'm going to do is I'm going to mark my sine terms and gather them up so that I have, let's see, this sine, I think I'll just leave that as the right-hand side because it doesn't have any coefficients on it. Then I can equate coefficients. So the sum of the coefficients on the left will be 1 for the sine and 0 for the cosine, and similarly for the bottom. So gathering up my sine terms, I've got minus a1 plus a2 minus 2b2. Minus a1 plus a2 minus 2b2, all that multiplies sine t. Now did I get the negatives? I didn't. Shoot. That's a minus, because I got to subtract it to the other side of the equation, and that's a plus. So minus a1 minus a2 plus 2b2 sine t. And now we go after the cosine. Well, the cosine terms, I've got an a2 minus this a1 plus this 2b1 times cosine t, and that equals this vector. Oh, I've run my two lines together. This can be easier to follow if I clean it up. Your paper probably does not look like mine. So that equals the right-hand side. Okay, let's get the bottom one. All right, sine terms. I've got a sine here, and here, and here, and all that's got to add up to, well, 0, because there's no sign in the bottom. Minus b1 plus 3a2. That would be minus 3a2, because I have to subtract to get at the other side of the equation, plus 4b2. And cosine terms are b2. Okay, minus 3a1 minus 4b1 and that's equal to minus 1 times cosine t plus 0 times sine of t. And now I have a system of equations. Minus a1 minus a2 plus 2b2 adds up to, that's the coefficient on sine, which must be minus 1. The coefficient on cosine is 0, and that is minus a1 plus a2 plus 2b1, and that adds up to 0. Down on the bottom, I've got minus 3a2 minus b1 plus 4b2 and that adds up to the coefficient on sine on the right hand side is 0. And then the last one is minus 3a1 minus 4b1 plus b2, and that adds up to minus 1. Okay, 4 variables for equations should work. Now, of course, the catch is that, you know, there's a bushel of arithmetic before this. So if any tiny little error crept in, then this system is not the one we want and could be garbage. But at least we can demonstrate the method. What I would do at this point, there is no way that I would try to solve this by hand. This is just, now, you know, if I were trapped on a desert island and some evil genius said, you can get off this island if and only if you can solve this system of equations without the aid of technology, well, then I would keep at it until finally I solve it. But since we're not in that situation, I am definitely going to use technology. So I've got a 4 by 5 system of equations, and A1 is minus 1 for A2. The B1 there is 0. The B2 is 2. And all that adds up to minus 1. Okay, minus 1 for the A1 column, 1 for the A2 column, 2 for the B1 column, 0 for the B2 column, and that adds up to 0. Minus 3 is the coefficient on A1. There's a 0 on A2, a minus 4 on B2, a 1 on B2. I said it wrong, but I typed it right. And minus 1 on the right-hand side. And finally, minus 3, 0, minus 4, 1, minus 1. Okay. Minus 1, 0, 2, minus 1. Minus 1, 1, 2, 0, 0. 0 minus 3. Whoops, that's not what that says. Got an error on the third row. Minus, what if I got offline here or something? Okay, good thing I checked. Third row should be 0, minus 3, minus 1, 4, and then 0. Then -3, that's correct. 0, -4, 1, -1. That looks okay. Okay, where were we? 0, -3, -1, 4, 0. That looks right. -3, 0, -4, 1, -1. Okay, so we are now ready to try to solve the system. And that's discouraging, but you can scroll over to the right and see what we have here. I recognize these. That's 3 and a 6, 5 and a half, -1 and a 6, and I'm not sure what that one is. But you get some numbers, right? And those are the numbers that go in here, 1, 2, 3, 4. But I'm not writing anymore because frankly, I don't believe them. I worked it out once before and I got integers. So there's some little error in here, and yeah. But you have the method. Okay.
I think the error is that there's a -4 B1 in your second person.
Right there.
And you're below it, like in that function. You didn't feel positive.
Oh, right here. So that would be a plus. And then that was the fourth equation here, right?
Yeah.
So that would make this a plus. That's actually very easy to follow up on since it's in the calculator already. So 4. Let's see what this does. Looking better. So who knows? That might be correct. But those are the coefficients A1 and A2 that go here. And the coefficients 0.7 and 0.1 would go here and here. And that's the particular solution. The homogeneous solution, just like we did before. C1 x1 times e to the lambda 1t and C2 x2 e to the lambda 2t. And I think I want to let that one rest. Okay, so that is a demonstration of the general approach anyway for how to solve equations that are non-homogeneous. There is also a variation of parameters method for systems of equations. It's not always horrible to carry it out. Sometimes it is, but of course, sometimes undetermined coefficients is pretty challenging too. But the reality is that in practice, it's more helpful to know that such things can be solved than it is to know how to solve such things. Because in realistic situations where you've got to get the numbers so that you can design the machine or design the circuit or whatever the predict the behavior, you're going to be doing that with a software system anyway. So Okay, now predator-prey systems. Here's a situation where things are really quite different from something like designing a circuit or predicting the behavior of a mass spring system or trying to solve a mixing problem or something like that. In those kind of situations, we expect that our differential equations will closely model the physical behavior of the system. And the reason we want to solve the equation is we'd like to be able to get hard numbers out of it. In something like a predator-prey system, oftentimes what we're really more interested in is a qualitative solution. And what I mean by that is we'd like to know generally how this system behaves. So, so suppose we have, I don't know, rabbits and wolves in some ecosystem, and the wolves eat the rabbits, and the rabbits eat plants. So what tends to happen are behaviors like this in a big sweeping sense that isn't very helpful for predicting what's going to happen in any particular case. Is if you get massive numbers of prey animals, then, you know, like the next season, you get huge numbers of predators start to go, right? And at least over time, over enough generations, you have so many predators that they depress the population of the prey. As soon as that happens, well, now the predators aren't getting fed very well and their numbers go down, but then that allows the prey animals to come back up. So you can see there's kind of a balance. For these kind of problems, I tend to either pick examples from some other source or nudge examples, because it's very easy to cook, you know, you just write down some numbers and you'll generate a system that doesn't have nice behavior at all. And by the way, a lot of systems work like that. You introduce a certain kind of animal into some ecosystem, and either their numbers just run completely out of control, becomes a nuisance invasive species, or every time you do it, the population just collapses and, you know, they die out. Well, that can happen with these systems too. So I have actually picked these from sources. I'll tell you what I did. I typed it into Google and I picked some videos because I thought these are common things. Then if my students would like a follow-up, they can do what I did. And you know, you can find lots of these on YouTube at Khan Academy and stuff like that. But we're mostly interested in just looking at the general behavior of these and learning a couple of techniques. Okay, so first of all, I want to point out that we have the derivatives on the left-hand side. One of these equations is going to be for a predator and one of them is going to be for prey. This term over here, notice this is nonlinear. It's an x times a y, or as we've been writing in the past, it will be y1 times y2. So this is strictly a nonlinear equation. However, nice nonlinear equations act like linear equations locally. In other words, if you look at its behavior at some point and you just move a little away from that point, you can sort of predict what's going to happen in a linear kind of way, and things do work. So what we're hoping is that interesting points will be like interesting points for linear systems. In other words, you could have a stable node, you could have an unstable node, you could have a stable, asymptotically stable spiral, you could have an unstable spiral, all of that kind of stuff. So in this case, the thing to focus on first is what's known as the interaction terms, the x times the y. Now in this case, it's negative. So you can see that for the y here, if the x starts getting bigger, that's going to cut the growth of y, because that's a derivative there. On the other hand, over here, we're looking at x now, if the y starts getting bigger, that's going to enhance the growth of the x. So it looks like the x's benefit in the sense of getting a larger population if the y's go up, and vice versa for the y's. So that would lead us to the conclusion that the X is modeling the predator and the Y is modeling the prey. And I'm basing that on the sign of the coefficient on the XY term. When it's plus, it's the predator. When it's minus, it's the prey. Now over here, we have some other terms as well. So X prime equals minus 0.05X. What that means is increasing numbers of the predator tends to depress the growth rate of the predators. And that actually kind of makes sense, right? You get too many predators, then they don't have enough to eat. So this is something like a competition term here. It reflects competition. But if these are two species, it's intra-species competition, not interspecies competition. Interspecies competition is coming over here. This, on the other hand, says that, well, if we're talking about rabbits, we're looking at their growth rate, ignoring prey, their growth rate is proportional to the numbers. That's exponential growth. So this looks like exponential growth here. And this kind of makes sense. If you have a bunch of rabbits, they tend to multiply very rapidly unless you have something that's depressing the population, like a predator. So this all makes sense here. Now we could ask ourselves this question: are there any places where this system is in equilibrium? Well, the system is in equilibrium if the growth rate of the X and the growth rate of the Y is zero. It's in a steady state. It's in a steady state then. It's neither growing nor shrinking. So what you do is you set X prime equals to 0 and Y prime equal to 0 and solve for X and Y and see what you get. So I'll say X is equal to minus 0.05X plus 0.001 XY, and 0 is equal to 0.1Y minus 0.005 XY. And I notice on this one, there is a common factor of X. On this one, there's a common factor of Y. So I'm going to take that out, but I'm also going to, what I'm going to do, these are pretty inconvenient coefficients. So what I'll do on both of these lines is just scan for the smallest one, and I'll divide that out. So I'm going to divide out 0.001, which is to say I'm going to multiply the rest of it by 1,000 and take off the X. And then if you multiply, the reciprocal of that is 1,000. So 1,000 times 0.05, well, you move the decimal point 3 places, 1, 2, 3, 50. But there's, the X is gone, factor off, plus Y. And on the bottom one, same deal. I'm gonna divide out the 0.05, and there's a common Y, so I'll take a Y out. And in this case, I suppose I can figure it out. But this is why we have machines. So I have 0.1, and I want to divide that by 0.005. And I get 20. And I've taken off the Y. And then 0.005, dividing it by 0.005 gives me a 1, but that was a negative here, so I want to preserve that. And the Y is out, but the X is still there. And these are both, just for emphasis here, it's already there, but those are both set equal to 0. So I'm looking for a simultaneous solution. And what we know is that if X is 0 or Y, really? Oh, look. There's a minus here. and there's no minus here. So put it back in. Okay, now I believe it. Or y is 50, that first row will be 0. If y is 0, or x is 20, then the second row will be 0. Now, in order to look at all the possible solutions of this system, what you have to do is pick one of these and match it with one of those. Because I got to force the first row to be 0, and I have to force the second row to be 0, but any possible way of doing that counts. So let's start with this one. X is 0, y is 0. It's a pair. I'll emphasize that with parentheses. That's a perfectly good solution. I take x is 0 from the left part. I take y equals 0 from the right part. Now, if I take x equals 0 from the left part, I cannot take x equals 20 from the right part, right? So that match doesn't work. If x is 0, I'm forced into choosing y is 0 on the right. On the other hand, I could take y equals 50 on the left. If I do, then I can't choose y equals 0, and I'll have to choose x equals 20 on the right part. So it looks like I only get 2 solutions there. So there's a trivial solution which says this: if you have absolutely no wolves and you have absolutely no rabbits, then you'll stay there. Gee, thanks so much. You know, we really needed to know that. This says if you have 20, by the way, I don't think this is very realistic, at least not for wolves and rabbits. If you have 20 wolves and 50 rabbits, you'll tend to stay at that spot. Now, if this is a stable equilibrium, then what that would mean is, you know, if you lose some rabbits, then that would nudge the system, but it'll tend to go back towards being a stable equilibrium. It'll go to this attractor. On the other hand, if it's not a stable equilibrium, then, you know, if you nudge it a little bit, it's going to do something very different. And that's the case over here. This is the x equals 0, y equals 0 is absolutely not stable. You put a pair of breeding rabbits in there and nothing else, guess what? Things happen, right? So let's take a look. Let's take a look at what we get when we look at the phase diagram. So what's the website? Wolfram. And it's just waiting for a command here. So stream plot, if I can type it, stream plot is what we're after. And now what I'm going to do is simply enter this, these equations that I had. X prime is equal to minus 0.05x plus, you guys aren't seeing it, are you? I will type this in while we're waiting. For those of you online, I've got to get the classroom switched over to the screen share. Okay. Getting there. Okay, now everybody's looking at the same screen. All right, the system was minus 0.05x plus 0.001xy, comma, 0.1 y minus 0.005 xy. And we know that we're looking for our equilibrium point around 2050. So x can range from 0 to, I don't know, let's try about 40 to start with. And y can range from 0 to 75 or so. Okay. And it's kind of a little window they give us, but it's helpful. You can see that down here along this axis, now this would be saying what? We have a very small y and we have a large x. Well, x, we said those are the predators. So let's suppose you have lots of predators and few prey. What happens? The number of predators collapses rapidly, right? And then over time, as the predators start getting very small in number, then you start up here, and that's giving you a small number of predators, but lots of prey. And if you started really low here, this is going to shoot way up before it finally cycles back around here, but it will. And if you're over in this region, you can see it a lot easier, the overall behavior. Going to cycle around, and it actually spins down into that stable point. So this is a stable spiral. And we saw that with linear systems. And that's the reason for looking at it in linear systems, is you could see that you can have some understanding of the qualitative behavior of nonlinear systems. So we're doing some analytical things here. We actually computed the coordinates of the equilibrium point, but then it's really the technology that's giving us the insight of how this thing is behaving. So I think this is helpful. And you know, if you're a wildlife biologist, this kind of insight is useful. If you knew that this model was reasonably accurate, then you could predict, oh, we could sustain a long-term population of this predator and this prey species in this area. Okay, so that takes care of that one. Let me try to switch back now. Okay. All right, let's take a look at another one. Now, before I leave this though, let's just take a look at this. We have just the qualitative features. I don't care about the numbers. I've got a minus x term and a plus xy term for the predator. I've got a plus y term and a minus xy term for the prey. Now, on the next example, things are a little bit different. I've got a plus, for x prime, I've got a plus x, a minus x squared, and then a minus xy. Y prime, minus y, and a plus xy. Okay, now, first of all, in this case, can you see which one is the predator and which one is the prey? This is another predator-prey system. Which one grows at the expense of the other? Yeah, this one, actually, it's getting the expense, right? On the interaction term, it's negative. The growth rate is negative as the other species increases. So this looks like prey. And this then would be predator. And all I'm taking that from, it's not deep. I'm looking at the sign of the coefficient on the XY term. Now, there is a qualitative difference, though. Before, I had this kind of term and the interaction term, this kind of term and the interaction term, but I didn't have this X square thing. What that is supposed to model is there's some kind of limit to the growth of this population. Classically, it's usually described as like food supply or something like that. So, you know, there's only so many of these kind of plants that grow in the area that rabbits eat. So if their numbers get too big, they end up competing with themselves. So that would be this relates to what is called carrying capacity. This environment can only handle so many of these prey animals. And when you get more than that, they just, you know, there's not enough to sustain them. But, you know, there's other things that happen too. Like in, well, if you start growing algae in a container of water, what happens over time is the numbers, they don't just grow without limit and fill the whole container. What happens is they cover the surfaces and then they stop growing. Well, what's happening in that case is they're actually putting out waste products, and the waste products limit the growth. It also, with certain kind of algae, for instance, it triggers some metabolic changes. And I don't know if you ever tried to clean out an old trough or something that's had algae in it a long time. It's like calcified. It's really hard to get out. Whereas if it's recent growth, you put some bleach on there and rub it and it just comes right off. Well, the organism actually senses this buildup of waste products and it starts behaving differently. So there's feedback systems in it. And that's kind of what we have here, a feedback system, but it's a feedback system that limits the rate of growth of the population, not the behavior. Okay, so it looks like we've got prey and predator. We also have a carrying capacity term here. And now we would like to know, where is the equilibrium point? Or points. You know, in principle, there could be more than one. And there was more than one on the last one. We had one at the origin and then somewhere else. Okay, so we set x prime and y prime equal to 0. And scan across this and see if we can factor anything out. Well, we can always factor a number out. So we always take the smallest one, 0.0002 will do, and everything has an x. So I'm going to take 0.000, there are 3 of those. And do I have the sign the way I want it? I guess it would take an x out. And now, this term divided by that is 1,000 minus 0.00. Oh, that's the number I factored out. So that becomes a 1. And 0.006 divided by 0.0002. is 30. And that is, we're setting that equal to 0 because we want to know when is the, at what point is the prey neither growing nor shrinking the population. And likewise on this one, I'm going to factor out the 0.00008, and a y is coming on that. So we got minus 0.0015 divide by 0.1234 zeros and an 8, 18.75. And let's see, we're taking off the y, and that was negative, so it stays negative. And then this one, we're factored that number off. So that's 1, and we're left with an x. Okay, once again, we get one easy one and one more complicated one, and we're going to have to solve a system of equations here. We can see that for the top row, or actually maybe I should put it this way, for the x variable, if x equals 0, that forces x prime to be 0. On the bottom row, if y equals 0, that forces y prime to be 0. But these other pieces are left over, and we would like to know, can you get a solution out of that? Well, you can. Put these terms over on the other side, and you get x plus 30y equals 1,000. And this one is, that one's just straightforward, right? X equals 18.75. Okay, well, this one is going to vary the x or y value you get out of it, depending on how you pick the opposite variable. So let's start thinking through the possibilities here. We could have x equals 0 from the x variable. Then we could pair it with something from this line. Now, we could not pair it with that because we already got x equals 0. So it can't be 18.75, and that forces us to choose y equals 0. So there's an equilibrium point. Option number 2, we could choose y equals 0 on the bottom row. If we did, then x could be 0 as well, but we already got that one. If we chose y to be 0 in this row, this column, then we're getting x equals 1,000. X equals 1,000, y equals 0. And by the way, this says something physically. It says if you don't have any predators, then the carrying capacity of this environment is 1,000 of the prey. So, makes sense. All right, what else could happen? I think we've exhausted this row as a starting place. So the other possibility is we could take 18.75 for the x off the second row. If we do that, then that gives us an 18.75 here. So you just solve this linear equation. You take 1,000 and subtract the 18.75, which is the x, and then divide it by 30. And we get 32 about 0.71. More or less. So it looks like we got an equilibrium point out here where neither x nor y is 0. We get an equilibrium point with a very large x if there are no predators. And of course, the origin is also a equilibrium point. So let's have a look at the phase portrait. Okay, I've got positive. Point 2x, and then I've got a new term entirely, minus 0.1232x squared minus 0.006 xy, and y prime is minus 0.015y plus that means nothing useful anyway, plus minus 0.15 plus, I need 4 zeros here. Well, and a knee, yeah, positive. Okay, and where's the action? Well, around 2030. So that's not an unreasonable window to start with. Of course, there's that one equilibrium point that's way off the scale, but let's see what this gives us. Okay. X is 18.75. That's back in here somewhere. Y is 32.71. I'm not seeing the one I'm expecting, but let's expand. Still can't see a lot, can we? Okay. I can't, I don't have enough of a picture to see. Do we have a spiral here? Or do we just have things swooping in and then turning back around? Now we're also expecting an equilibrium what? At around 1000x and 0y. So let's take a look for a really big x. Oh. So we're not getting a plot along here, so I can't really tell. What this would look like is you'd see an arrows pointing this way up to the 1000, and then arrows pointing back this way, back to the 1000. But I'm simply not getting a plot there, so I don't know. This is looking like perhaps an equilibrium. Up in around over 500 on X. And well, that could be the 18.75 on the Y. Well, let's switch back here. Is this accurate?
It's 187.5. So
I did,
the decimal point would have to be right.
on this one?
Yeah.
Oh, okay. 187.5?
Yes.
Well, that would certainly make a difference, wouldn't it? So then we got 187.5 on X here, and the Y is going to be utterly different. That gives me a Y of around 27.
Did you mean to change the Y to 30?
I'm not sure what you're looking at.
On just the range?
Oh, well, I'm not getting anything in this. I'm not getting any interesting point in here, right? So,
Don't you have to expand the X range for it? Because if it's 187.5.
oh, yeah. Oh, well, it's hard to say, isn't it? From that plot, there might be something going on in here.
Could you push up the lower end of the X range on that so you can?
Yes, we can. Whether it will help much, I don't know. I'm not sure how to interpret that. Coming in here, going, I don't think so. This is, oh, right there is our equilibrium point right there, right? 187.5, would that work? And 27, yes. Yes, that looks like it could be. Equilibrium predicted by the equation. Actually, I might almost sneak it in here. Right there. 187.5, and that's not an unreasonable estimate for that on the X, and around 27 for the Y. Yeah, could be. It's hard to pick out from the diagram. Now, keep in mind that this is sort of like the free online version of Mathematica, and Wolfram wants you to buy their software. So if you buy the hugely expensive software and you have a full screen plot, then it's going to be a whole lot easier to see what's going on. But there's some appeal to free as well. So that's why I'm using that one. So we do get some interaction here between what we're doing with our equations and what we're doing with the technology. And honestly, I think that equilibrium point, I remember now why I included this one. It's hard to pick out unless you know to look for it. It's hard to see in the plot, but it is there. And also, it alerts you to this other one that's absolutely invisible in the plot. You cannot see it. But anyway, we got it. I think, oh, one last one, and then we'll be done, and we'll be out of time too. This one right here is not predator-prey. And you can tell that because you've got a negative XY term for X prime, and you also have a negative XY term for Y prime. So this is not predator-prey. What this is a model of competition. Now, we've seen competition before in intraspecies, but this would be interspecies competition. And by the way, it's not just animals or plants that behave in this sort of way. In physical chemistry, for instance, if you have you can have two reactions going on in the same container that compete with each other. So, perhaps this would be a model of one of those as well. Okay, well, how do you analyze these things? Well, first of all, because of this competition behavior of the system, we really do expect some stable solutions. Wouldn't it make any sense for either one of these to get totally out of control? Because if X, suppose Y is moderate and X gets really huge, well, you're going to be pulling down the derivative with an X squared term. So this is clearly going to dominate that. And if Y is moderate and X is huge, it'll also dominate that. So if X gets too big, it's that population starts to shrink, and the same argument goes for here. It's just you're nudging a little bit the values, but the overall behavior is the same. So surely there's a stable solution. Now maybe it's 0, 0. Maybe this spirals in or collapses to 0, and you just can't prevent that. But we can find out in the usual way. You set X prime equal to 0, and we have X's common all the way through here. 0.001 is the smallest coefficient. So we'll factor off 0.001x. And when we do, we get 500, just 500, the x is gone already. 0.004 divide by 0.001, well, that's 4. Minus 4, and 1x is left. We've got 1 on the outside. And then taking off 0.001 there, we're just left with 1. And we do have a y though. And that's going to be set equal to 0. And if we set y prime to 0, then we can factor a y off, and 0.001 is the smallest. So 0.001y times 400. So we get here, if we're taking out 0.001, then that turns into a 1. And the y comes off, we're left with the x plus 2x equals 0. As predicted, x and y both equal to 0 is an equilibrium point, but then we have these two other equations. 4x plus y equals 500 from the first row, and 2x minus y equals 400 from the second row. And then we also have x equals 0 and y equals 0. And we have to think about the ways you could mix and match these. And then you could have a simultaneous solution from that. Yeah, problem?
Why is it a 2x?
Right here, because I have a 2x there, and I don't know if it's right. I factored 0.001 out, and this is twice that. It's,
Would it be minus 2x?
let's check. We should have plus, minus, minus, plus, minus, minus. Thank you. So when you push them both to the other side of the equation, 2x plus y equals 400. Yeah. Okay. Equilibrium points of the system. Clearly 0, 0 would work. Option number 2, if we matched x equals 0 from the top row with this other linear equation on the bottom row, then we'd have 0 for x and 400 for y. If we matched y equals 0 on the bottom row with this equation here on the top row, then we would have 125 for x and 0 for y. And then there's the possibility that we choose these two constraints together on the for the first and second row. Let's say subtract equations then to figure out the simultaneous solution. If I take 4x minus 2x, I get 2x. Y minus y is 0. 500 minus 400 is 100. And so x equals 50. If x equals 50, then you'd have 100 here, and then y would have to be 300. So looks like a good start. Okay, let's go for the phase portrait. So x prime equals 0.5x minus 0.0004 x squared minus 0.001 xy. 0.4, so we want on y here, minus 0.001 y squared minus 0.002 xy. And I hope that's sort of kind of close. Now, there's a lot of stuff going on here, so I don't know whether we'll be able to see it in that little tiny window all at once. But x's, let's let them range about up to 500, and y's, oh, maybe 500 as well. You got a square plot to start with. See what we have. Okay, well, certainly interesting. 0, 0, of course, is in there. Now, it looks like we would have a equilibrium point on both the X and the Y axes. On X, about 125, and that, you're kind of seeing a hint of that here. What we really would like to see is a straight arrow coming up this way and a straight arrow coming in from this way. But they are not plotting that one, but we do see it here, 125, 0. We also should see 0, 400. Whoops, I bumped that. Okay, it just redrew. 0, 400 or so. Yeah, they're not drawing in quite that close, but there should, it's believable at least that you would have a fixed point along here somewhere. And then 5,300 we were expecting. 5,300 is up in this area right here. And yeah, possibly so. Let's contract this and this. Yeah, there's something happening in here. 50 would be right in here. 300, yes, it's believable. So right where you see those two arrowheads coming together is the other equilibrium point. So it's there. All right. That was example 7, and I had 7 examples chosen, and I'm just about out of time. So that will do it. The homework for this, I'll post something on the on Blackboard, but the primary things that you want to know about these are, first of all, be able to tell when you're looking at one of these systems, you should be able to look at this and say, oh, I'm looking at a competitive situation rather than predator-prey because I got 2 negatives on the XY. Or if one's negative, the other's positive, you're looking at a predator-prey equation. If you have the negative x squared and or y squared terms, that's a carrying capacity term. And if you don't, that's just not a part of the model. And then you should be able to find equilibrium points. Obviously, trying to draw those phase diagrams by hand is be an exercise in frustration. And then finally, we have done a number of solutions of non-homogeneous equations, and clearly you or I could come up with an equation that the other couldn't solve accurately in a reasonable amount of time because it's just too darn messy. So you should know the general techniques, and for problems that have been cooked up to have reasonably nice answers, you should be able to get them. But at that, we're done with systems of differential equations. So next topic, I think on the list is Laplace transforms, but they're in there somewhere. Oh, could be infinite series. Those are fun too. So one of those two next time. And the exam is next week on Thursday. So you want to be preparing for that probably over the weekend.
So the exam will cover up from the first exam all the way up until today.
That's correct. To repeat the question for those online, the second exam covers the material since the first exam. And I will be grading for hour after hour over the next few days, and you'll be getting your papers, outstanding papers back. I hope over the weekend. That's the plan. So you have some feedback. But certainly there will be keys posted for the remaining homework assignments. All right, I'll see you on Tuesday.